So let's look at mill setup, one tool alignment and coordinating. We'll start with a single cutting tool in a mill, then build upon the challenge in Unit 2 with several cutting tools. The first task is to mount the vise, then align the spindle over a datum point PRZ. Manual mill indicator practice is invaluable in performing this task. There are many setup tasks performed with a dial test indicator. Once a spindle is located directly over the PRC or the known distance from it, then you must load the position into work coordinates. From that point onward, the work coordinates then reflect the actual XY position of the cutting tool relative to the PRZ. For aligning a hole entering the position, often a tool maker will place a precision 1/4 inch hole at a setup point. Your job is to position the spindle directly over it, then enter the location into the work coordinates. This gives you an idea of what that could look like in this figure. For edge alignment, a common datum PRZ is the intersection of two edges on two edges or one edge and one vice jaw. And so we can be thinking about that. How do we line over an edge? An indicator produces better accuracy than an edge finder. So here we can be looking at the locating over an edge. You read 0 in both positions, and ground parallel forms reverse counterpart. And so those are some possible things to be thinking about. So for the Z-axis PRZ, after setting X and Y PRZ, the cutting tool is loaded into the spindle, then brought to the location in the document that represents Z 0.0. This can be accomplished in two ways: touching off, physically touching the surface with a tool or a feeder of known thickness, or you can have an electronic tool probe or preset tools. Once the Z0 location is detected, it is then loaded into the work coordinate Z or length compensation offset that depends on the comp method next. So for a physical PRZ location, in many shops, the PRZ is set as we've just described. Locate the spindle at the position relative to the setup, then load the work coordinate page to read 0, X, Y, and Z, or the known distance relative to PRZ. Let's call that the physical coordination method. But there's another way to set PRZ points. A single setup can have more than one XY reference 0 point. So for example, looking down on the mill table, two vices are bolted in place and indicate true to the X-axis. Next, the spindle is located over the corner of each vice in turn. Then the machine coordinates are read for each reference point. Those coordinates are loaded into fixture offset memory, usually G54 through G59. Fixture offsets actually start at G52 or G53, the first one in the control, but that base offset is usually kept loaded with zeros for two reasons: referring to a simple way to get back to the machine home, plus it is global, changing that base offset change all other fixture offsets by the same amount. They are linked to the base. So here you see G55 and G56, giving you some context there. So I'll just finish with this and then we'll pause. Summary for fixture offset: as before, the spindle is located over P or Z at a known distance from it. But this time, the machine coordinates of the spindle position relative to M/H are noted and loaded into a fixture offset memory, G55, G56, and so on. So calling out G55 in the program sets the PRZ at vice 1, then G56 sets it to relative to vice 2. After reading G55 and G56 in the program, your work coordinate screens will be read the spindle's position relative to whatever vice has been called out. So a key point is to maintain consistency. Some shops use fixture offset even for a single vice setup. Okay, we'll break there and then we'll finish up